Hi, this is John Whitaker for the Mathematical Analysis class, and this is our 15th video lecture. And we are working with basic topology, and our subject matter at this time is about compact sets. And so I want to look at a theorem, several theorems today about compact sets. First one states that compact subsets of a metric space are closed. Okay. So, to prove this, let's let K be a compact subset of a metric space. What we're going to do is, well, let's give the metric space a name. Let me start that way. Call it X. What we're going to do is we will show that the complement of this compact set is open, and therefore K itself has to be closed. All right, to do this, let P, let's pick a P that's in X, with P not being in K. Okay. So that means P is in the complement of K. We want to show P is an interior point of the complement. Okay. So with P not in K. So here's what we do. If Q is an element of K, we let the set V sub Q comma P and another set associated, W sub Q, be neighborhoods of P and Q respectively, of radius, each having radius less than 1/2 the distance between P and Q. Okay, now what we do is we think of each Q in K, okay, and we form these sets for each Q in K, these neighborhoods. And then what we notice is that K is going to be contained in the union of all the Q's in K of WQ, which we'll just call W. Well, I made a mistake. I don't call that W. Let's just let it be called what, let's not give it a name, is what I should say. But what we can say then is that the WQs this collection, Q being an element of K, is an open cover of K. Each WQ's neighborhood, so it's open, and their union contains K. Since K is compact, what that meant that every open cover has a finite subcover. So there exists a finite subcover of K from this collection. Say, let's call it W sub Q 1, W sub Q 2, all the way up to W sub Q n. So what we're saying is that K will be contained in the union as I runs from 1 to n of these WQ sub i's, which let's label that set W. Now, remember, for every one of these W sub QI's, or W sub Q, there was a corresponding set, this V sub QP, okay? So, here's what I'm going to do. I'm going to let's give it a name. Let V be equal to the intersection, as I run from 1 to n, of the V sub QI P's. Okay? Now, the V sub QI's P's, they were open, they were neighborhoods. And so here's what I want to tell you. If you intersect them, a finite intersect of open sets, that's open. So what we have is V is an open set which does not intersect W, so let's stop for a second. Why doesn't it intersect W? Well, let's say that something was in W. To be in W, it's got to be in one of these WQ sub i's, okay? But this V sub Q, let's call that particular one that's in W sub Q I naught. But the V sub Q I naught P has no intersection with that guy, so they don't overlap. Okay, so it can't be in that particular one, so it can't be in the intersection of them. Okay? So that's how we see that those WV have no intersection. Okay? One other thing, though, I want to say is that P is an element of V. Now, why? Because remember, these V sub Q sub I P's, that's a neighborhood of P. Fine. So before I write up the rest of it, let me get the idea. See, what's happening is we got this set V, P is contained in V, and V doesn't intersect W. So that means V can't intersect K either. So that that means that V has got to be contained in the complement of K. And so since V is going to be open, that means P is an interior point for the complement of K. And P was arbitrary. That's going to be how we show that K complement is open and thus K is closed. Let me write that up. So here, a little bit more details. Since V is open, then there exists an R greater than 0 such that n sub R of P, that neighborhood, is contained in V. What it means for V to be open and P is in there, which is going to be contained in K complement, because V doesn't have any intersection with W and K is contained in W. So P is an interior point of K. Now what was P? P was just some arbitrary element, of K complement. What was P? P was some arbitrary element of X that was not in K. So P was some arbitrary point in K complement, and it's an interior point. So all the points of K complement are interior points. Thus, K complement is open. So K is closed. So if you're compact, you're closed. So that ends that proof. Okay, I now want to look at another theorem. And it's easy to state. It says closed subsets of a compact set are closed. I'm sorry, are compact. Okay, let's look at the proof of that. So proof, suppose we have F being a subset of K, being a subset of X, where X is a metric space. K is compact, and X, and F is closed. Is closed, and we mean in X. All right. So what we're going to do is we're going to let V sub alpha be an open covering of F. Okay. Now, what we're trying to do is show that F is compact. Okay? That's what we're trying to do. Okay. So, if we look at the collection of sets, let's call it capital Phi here, it's got F complement and all the V sub alphas. That's it, alpha is element of A. So it's all of these sets union this one. Okay? So that's what's in big Phi. Then this is an open cover of K. This covers F, this covers everything outside of F, so you union them up. You're going to open cover of K. So since K is compact, Phi has a finite subcovering of K. Okay? Let's call it phi star. Okay? Now, what I want to look at is if F complement is an element of phi star, okay, remove it, and what we're left with is a finite subcover of F from the V sub alphas. Okay. If this phi star does not include F, then phi star itself is a finite subcover of F from the collections of the V sub alphas. And so that means F is compact. And so that ends that proof. We have a corollary from this that we're going to look at next. Okay. Here's what it says. It says if F is closed and K is compact, then F intersect K is compact. Let's do a proof of this. Okay. Well, we'll let F be closed and K be compact. Okay. So since K is compact, K is closed. Okay, therefore, F intersects K, that's the intersection between two closed sets, and that's got to be closed. So, since F intersects K is contained in K, that is, we have a closed set, subset of a compact set, then, by the previous theorem, F intersect K is compact. Okay, here's another theorem. If case of alpha is a collection of compact sets of a metric space X, okay, such that the intersection of any finite subcollection of the case of alphas is non-empty, it's non-empty. So anytime you intersect any finite number of the case of alphas together, you get something that's non-empty. Then the intersection of all the case of alphas is going to be non-empty. Write that up. And this proof is going to be by contradiction, I believe. Yes. So, proof by contradiction. Okay, so we start off by saying let case of alpha be a collection of compact sets from X of X such that, so this is a metric space, such that every intersection of finite number of the case of alphas is non-empty. All right, so we're doing a proof by contradiction, so let's suppose the opposite of what we're trying to prove. So we're trying to prove that the intersection of all the k alphas can't be empty, so it has to be non-empty. But what if it was empty? So it equals empty set. Let's suppose that. All right. Now here's what we do. We start off by fix a case of 1 that's in our collections of case of alpha. So just take one particular one of them, okay? Since we are assuming that the intersections of over all the alphas in A of the K alpha equal to the empty set, since we're assuming that, then what that means, no point of K, so 1, can be in all the other case of alphas, because if that point from case of 1 was in the rest of the case of alphas, the intersection would not be equal to the empty set. So what that means is, for each point P, element of K, there exists one of these case of alphas. I'm going to call it case of alpha P. So for that particular point in K, there's a case of alpha P such that P is not an element of K sub alpha of P. So that means that P is an element of K sub alpha sub P complement. Now the case of alpha of P, remember, it's compact. So if it's compact, we know that it has to be closed. So the case of alpha P complement has to be open. Note, the case of alpha sub P complement is open. Okay. Now, if you do case of alpha P for every P, okay, in case of 1, what you get the case of alphas complement, alpha being different than 1, forms an open cover of case of 1. Give everybody a second. Okay, yeah, makes sense. So here's what's happening. You see, P is in case of 1. And then you get this guy, case of alpha of P. It doesn't have P in it. So its complement does. So these guys are contained in this collection of open sets. And it will cover all of case of 1. Okay? Because P is, each P in case of 1 will be in one of these. Okay. Well, great. The important thing for compactness, it allows us to go from having infinitely many situations, infinitely many sets to deal with, to only finite many. So, since K sub 1 is compact, then there is a finite subcover of K sub 1 from the case of alpha complements, alpha being different from 1. Okay. And we're going to call them, say, case of 1 complement, we'll call it alpha sub 1 complement. K sub alpha sub 2 complement, all the way up to K sub alpha sub n complement. Okay, so that covers K, or K sub 1. So what we have is that K sub 1 is contained in K sub alpha sub 1 complement union, K sub alpha sub 2 complement union, all the way up to union K sub alpha sub n complement. So that means that K sub 1, if you intersect it with this guy's complement, okay, intersect it with that guy's complement. So K sub 1 is contained in here. Well, look at the complement of this. Okay? And so nothing in K sub 1 will be in here, so that intersection would be, I think I'm off the board here. Oh gosh, I didn't turn them. I'm sorry. Okay. So all I did was, I wrote down, sorry, that we had that the K sub 1 is contained in these, the union of these K sub alphas sub I all the way up to n's complements, because that was a finite subcovering, okay? And so what I was saying here is, since K sub 1 is in this union, or in this set, let's just think of it as one set, then if you take a look at the complement of this set, that's what I'm doing here, and intersect it with K sub 1, there isn't anything in common. So this is equal to the empty set. Okay, but let's look at this set a little bit closely. So that means K sub 1 intersect, what is this union of a bunch of sets complements? That's going to be K sub 1 intersect K sub alpha sub 1 intersected with K sub alpha sub 2. This intersect will be, that's what it's going to be. Intersected with intersection of K sub alpha. That's what this previous line is going to be equal to. And that's equal to the empty set. But that contradicts our supposition, one of our hypotheses, that any finite collection of the K sub alphas, if you intersect them, you get something that's non-empty. So we must have assumed something wrong. So that means that what we assumed was that the intersections of the K sub alpha was equal to the empty set. So this intersection must be non-empty. And that proves it. We're going to look at a corollary of that next. Excuse me. So corollary we'll look at next. In particular, if K sub n is a sequence, so here again, 1 to 10, is a sequence of non-empty compact sets n plus 1 is contained in the case of n, and this is for each n element of the counting numbers, then the intersection into 1 to infinity of the case of n is non-empty. So let's look at its proof. Okay. So let's first of all note for the collection case of n of non-empty compact sets, with case of n plus 1 being contained in case of n, then it's really this characteristic. Then, this last characteristic, any finite collection, any intersection, I should say, between finitely many case of i's, if you will be non-empty. Okay? As if you look at case of n sub 1, intersect case of n sub 2, intersect case of n sub j, let's say. Okay. That will be contained in, or be equal to, case of n sub naught, where n sub naught is equal to the minimum between n sub 1, n sub 2, all the way up to n sub j, because of the characteristic, the case of n plus 1 is contained in case of n. Okay, thus, by the previous theorem, what we have is the intersection between all the case of n's will be non-empty. That is this proof. Okay, I want to look at least two more theorems. So here, if E is an infinite subset of a compact set K, then E has a limit point in K, and we'll do this proof by contradiction. Okay, so we're going to let E be a subset of K where E is infinite and K is compact. Okay. So we're going to suppose that no point of K is a limit point of E. Okay. All right. So what that means for each point, let's say Q in K, there exists a neighborhood of Q. Okay, let's give it a name. Let's call it N sub RQ of Q, such that N sub RQ of Q intersects E in at most one point namely Q. Okay. All right, that's what we have. Now, here's something to observe. The K is going to be a union. I'm sorry, K is going to be contained in the union for all the Q's and K's of N sub R sub Q of Q and the N sub R sub Q of Q are open because they're neighborhoods. Okay. So what that tells us is that these N sub R sub Q's of Q form an open covering of K. And so, since K is compact, then there exists a finite subcover of K from this collection N sub R of sub Q of Q. Say N sub R Q sub 1 of Q sub 1, N sub R q sub 2, q sub 2, all the way up to n sub r, q sub, let's say j, qj. Now, since E is contained in K, which is contained in this n sub r sub q1, q sub 1 union, n sub r, q sub 2, q sub 2 union, with this last one, or q sub j, q of j. Okay. And each n sub r, q sub whatever, let's say I, q sub I, contains at most one point of E. Then E has to be finite. But we were assuming that E is infinite. So that's a contradiction. So that means E must have a limit point in K. And that is that proof. Okay. We have just enough time to get to the next theorem. Here's what it says. It says, if I sub n is a sequence of intervals, okay, in R, such that the I sub n's, the I sub n plus 1 is contained in I sub n, and this is for all n element of the natural numbers, which we'll call it j. Oops. Then the intersection of I sub n's is non-empty. Now, we would have this result if from a previous corollary, if we knew that the I sub n's were compact, but we don't. Now, by I sub n, we don't at this point. They happen to be compact, but we don't know that. The I sub n's, to be an interval, means you're a closed interval. You contain your endpoints. Okay? So let's look at this proof. We let I sub n be equal to A sub n to B sub n. And we're going to let E be the set of all A sub n's. Now, the first thing to notice is then E is non-empty. And E is bounded above. by b sub 1. And that has to do with as a sub n plus 1 up to b sub n plus 1 is going to be contained in a sub n up to b sub n. So the first integral, if you will, is the biggest. Okay, now here's what we do. We let, so what do we have about E? It's a non-empty subset of the real numbers that's bounded above. Since the real numbers have the LUV property, that means, so the soup of E exists, call it X. Okay. Okay. Now, because the I sub n plus 1 is contained in I sub n for all n elements of J, then what we have is if m and n are elements of J, then A sub n is going to be less than A sub n plus, let's write this down here. So A sub n is going to be less than or equal to A sub n plus m, which is going to be less than, just strictly less than. I'll write down less than or equal to B sub m plus n, which is going to be less than B sub m. That's what we have. Thus, X is going to be less than or equal to B sub m for all m elements of J. So what we're saying is the right-hand endpoint, all of those are going to be upper bounds for E. So by the definition of X being the sup of E, A sub m is going to be less than or equal to X, and that's true for all m elements of J. Thus, we have that X is an element of A sub m to B sub m for all m elements of the counting numbers. And thus, X is in this intersection of the I sub n's, because that's what, or I sub m's if you want. Because X is in all of them. So that says that the intersections of the I sub n's are non-empty. That's what we were trying to show. Okay, that's enough for today. Thank you very much for your time and patience.